How does buckling cause catastrophic structural failure? Imagine a tall, slender tower or a long, thin column holding up a building. It looks sturdy, but under certain conditions, it can suddenly give way. That's buckling, a failure mode that surprises many engineers and builders. When a component like a beam or a column is compressed, it doesn't always break or bend gradually. Instead, it can suddenly bend sideways or twist out of shape. This quick change can cause the entire structure to collapse. Buckling happens when the load pushing down on a slender part exceeds a specific point called the critical buckling load. This load depends on the shape, size, and material of the part. Even if the stress in the material stays below its breaking point, buckling can still occur because it's about the stability of the structure, not just the material strength. The process begins when forces push on a long, thin member. Tiny imperfections like microscopic flaws or slight bends make the member less stable. As the load increases, these imperfections grow, causing the member to sway or bow sideways. Once the load hits that critical threshold, the member suddenly bends or twists out of its straight position. This abrupt deformation reduces its ability to support weight. Once buckling occurs, the load it was holding is suddenly transferred to other parts of the structure. If those parts aren't strong enough to handle the extra weight, the failure can cascade. This chain reaction can lead to the collapse of the entire structure in a very short time. Unlike gradual failures caused by fatigue or corrosion, buckling is quick and unpredictable. Several factors make buckling more likely. Long, thin, or tall members are more prone because they have less resistance to sideways bending. Lack of proper support or bracing makes it easier for buckling to happen. If the design doesn't account for buckling effects or uses materials that aren't stiff enough, failure becomes more likely. Also, if the load isn't applied directly along the center of the member, it creates bending moments that encourage buckling. To prevent this, engineers carefully analyze the shape and size of the parts. They use formulas like Euler's critical load equation to calculate the maximum load a component can handle before buckling. Design strategies include making the cross-section thicker or wider, adding lateral supports or braces, choosing stiffer materials, and controlling the length-to-thickness ratio to reduce slenderness. Understanding how buckling works helps prevent sudden, dangerous failures in bridges, buildings, pressure vessels, and aircraft parts. Because buckling can happen without warning and cause total collapse, it's one of the most important failure modes to consider during design and maintenance. Proper planning and analysis can keep structures safe and reliable, even under heavy loads.